In this video, we are aiming to achieve better knowledge about Euler's method, and we have built an algorithm. We have written a C++ program of a problem, and it will generate beautiful set of numbers. Our target to know from this video that what is Euler's method, explanation of Euler's method, algorithm to solve problem, write a C++ program of a problem. First, if we discuss the definition of Euler's method, that the definition says the Euler's method is a first-order numerical procedure for solving ordinary differential equations with a given initial value. Here, given initial value and ordinary differential equation. This is two-step, which is much more important here. And the Euler's method is a first-order numerical method. That means we will, in numerical procedure, we will find the many value of y function. We will find out the state of value of function, state of the value of the function here. Okay, this equation is our procedure that we will find out the better approximation of the function here, and this procedure is called Euler's method. If we consider a 2D Cartesian coordinate here, and this is our function y, here each of this expression is saying each of what, and here what is saying each of the expression in this equation. Here yn is saying that this one is our initial condition yn, and which is comes from xn here, xn, and this function is saying that this function is the derivative of our main function y, dy by dx is, and here h is the difference between two x value, difference between two x value. Here this difference is called h, and this h will be always constant here. That means h is a constant, and which will be x n plus 1 minus xn, and this will be our constant form. Okay, here this differential from the dy by dx, and that means function of x and yn is saying that we are going to plot a tangent line at the initial point, and this is our tangent line. This tangent line will be give us our next approximated value of our function, and which is yn plus 1 here. This tangent line will be give us next approximated function, and this next approximated value, and which is yn plus 1 here. Again we will draw another tangent line here, and which will be give us another value of y, that means our function, which will be yn plus 2, n plus 2, and again we will plot another tangent line which will be give another point, which will be yn plus 3, and so on. In this method we will find out what is our approximated function here, and this method is called Euler's method. What is Euler's method is saying? Euler's method is to describe method which give the solution in the form of a set of tabulated values at equally spaced point. That means each of the value of y will comes from equally spaced point of x. That means each of these difference will be equal here, and which is h. Consider a differential equation dy by dx is equals to function of xy. Here this function is this function here, and this function is allow us to plot a tangent line at that initial condition. An initial condition y(x0) is equals to y0. That means y0, if we consider n is equals to 0, then y0 is from x0 here. And this middle procedure, that middle method, is called our initial condition, y(x0) is equals to y0. Okay, if this initial condition and consider a differential equation, we are considering a differential equation is clear, you can make a comment in the comment box, and then I will describe furthermore if you want further more better explanation here. Okay, suppose that we want to solve the equation 1, this equation for y at x is equals to xr is equals to x0 plus rh, and this is saying that each of the difference, that this is x0 and this is x0 plus h, this is x0 plus 2h, that means this is x0 plus h, this is x0 plus 2h, this is x0 plus 3h. These are is representing that where is the function of where this r is representing that how much h difference we are go furthermore here for x value. Here this is x0, this is x0 plus 1h. Our next x value will be x0 plus 2h. Our for furthermore value will be x0 plus 3h, and it will be continue until we get the end of the value of x here. Okay, integrating one we obtain, that means we will be integrate this equation, first equation, and we will find our Euler's method by integrating this equation. Okay, now if we replace this dx from here to another side of the equal, then we will find that dy is equals to function of xy with dx. If we integrate this equation, y will be integrating from y0 to y1, y0 to y1, and dx will be integrate from x0 to x1, and this form will be give us y0 to y1 is equals to x0 to x1, and our dx here, sorry, our function of xy, which will be stayed as it is. If we go further more step, then we will find our first approximated value here. Y1 is our aiming. We are aiming to find the value of y1, that then we can build a better approximation. Then y1 minus y0 is equals to x1 minus x0, and function of xy, which is our equation. Then if we replace y0 on the other side, then we will find the first iterated value, but that means our first approximated value of our function y0 plus x1 minus x0 with function of xy. Here at initial condition, if we are assuming that the function of xy is this function of xy is our differential from at any point of that function, that xy means that it can be any point. If we consider, if in the Euler's method, we write tangent from our initial condition. That's why this function of xy is, we can assume that function of xy is equals to function of x0 y0 of our initial condition here. Then this equation will be turned into y1 is equals to y0, the value of function at initial condition, plus x1 minus x0 with the tangent at initial condition, which is our first approximation. If we continue this method, we will find our second approximation, which is y2 is equals to y1 plus x2 minus x1, and our next initial condition is x1 y1, and so on. And our general form of Euler's method, that is yn plus 1, which is our next y value of the function, with yn, our initial condition, plus yn plus difference between 2x, that is h, with difference between 2x, that is h, with function of x, y, and here xn and yn. This is our general form of our Euler's method. Okay, for geometric interpretation, for geometrically we can understand this, that our, if we consider this is our two-dimensional coordinates, Cartesian coordinates, and this is our function, which is y, and this is our initial condition, the function at the beginning. The value of initial condition here is yn, and this yn comes from xn here, and this differential equation is saying that we are going to plot a tangent line here, which is our first tangent, that is function of xn yn, our first tangent here. Okay, this tangent line will give us our first approximation. Here we are finding our first approximation, which is yn plus 1, and this comes from our this x value. Here x value will be x, here this is xn, here this is xn, our next x will be x n plus h. Again we will plot another tangent line from yn plus 1. For this tangent line, yn plus 1 is our initial condition, that initial value of our function, and this initial value, and we are plotted a tangent line from this initial value, and this tangent line will give us our next approximation of our next value here, and this is our next y n plus 2, and this tangent line will give us, and this point is from x n plus 2h. This here we are saying that our our x value is changing for each h here. Here h was 0, here h is 1, 1h here, 2h, and we are going forward with equally spaced value of x here. Okay, here 2 1 0, we can write these equally spaced points of x in general from, that is x n plus r h. Here r is equals to 1 2 3 and furthermore. And this is from here. Okay, if we continue this method, we will find a approximated values of function, and we are getting our approximated geometrical representation of Euler's method here, and this is called our Euler's method. Here this is called our Euler's method. Okay, now the algorithm part will be start here. In algorithm, first we are going to start, okay, and we will be define function of xy. What is our definition of we will be define our function, which function we are going to approximating. Then read values of initial condition x0 and y0. Here initial condition is much more important topic here. We have to specify what is the initial condition here is what is the value of x0 and what is the value of y0 here. Number of steps, we can add number of steps in our code, and calculation point will be xn. Xn will be our calculated point. Calculated step size will be h is equals to x1 minus x0 by b. This form will be give us how much step we will take for our approximation of this function. And here set I is equals to 0, and we will be use a loop. Here we are going to use a loop, and it can be any loop, which is while, do while, or for, any kind of loop you can use here, and display yn as a result. Here yn will be our result, which will be displayed in our terminal, and then we will be stop that program. And this is our algorithm for Euler's method. Hello.